I am going to start. So today I will be talking about generating permutations. This comes from Knuth's chapter in 4A, so combinatorial algorithms, very fun. I want to briefly touch on what a permutation is. And then there are two algorithms that are somewhat simple, mechanically simple to describe that Knuth describes, and then a bit more like further research. And I'm gonna go put you in do not disturb.
Oh yeah, my bad.
That's fine. Okay. And then I move the mouse. Okay. All right, permutations. So given a set or a multi-set S, a permutation will be any ordered sequence of every item in S. So just a quick review, a set is an unordered collection of any item. So it could be numbers, it could be words, it could be strings, it could be just an item. We have an unordered collection. Multi-set allows a repeat of any given item. So usually sets will always like contract down to the minimum set of distinct elements. Multi-set allow you to like redefine like inserting one multiple times, and then there's 3 ones in your set. So for n elements, there's n factorial possible permutations. If you think about it mechanically, if you want to arrange n items in a line, you have n possible choices for the first item, and then you have n minus 1 possible choices for the second, and so on. So you multiply those possibilities together, and you get n factorial possible permutations of your item. So when we get to enumerating permutations, surprise, there's n factorial things to output. So none of these algorithms are quote performant in the sense that we're not talking about real time anymore. Everything should be n factorial or worse. You're talking about like discrete subsets. Well, the thing that we can work on with algorithms for enumerating permutations is it would be nice if it's in some kind of order, so we can run it for a certain amount of time until we get to a permutation that we expect on the order. So a sorted order by like list of graphic characters is a very nice way to approach that. That will be the first algorithm that we talk about. The other version is minimal changes between permutations. So much like gray codes, only changing one value at a time in a binary string, we're going to try to make adjacent swaps. And so that's another way that we want to enumerate permutations kind of in a nice way. So algorithm will be slow. It'll take a while for large n. The other thing we want to achieve to minimize is minimum delay between outputting permutations. So you can imagine that your algorithm will have a print statement and have the permutation, or it saves it to an array, whatever. The amount of runtime in between outputting 2 different permutations would be very like nice and elegant for that to be minimized to constant delay, or usually we can expect linear time delay between outputting the permutations. So the first algorithm is going to be called algorithm L. So we'll talk about lexicographic permutation. So say we have the multi-set 1, 2, 2, 3. In this case, the lexicographic permutation is kind of read from left to right here, 1, 2, 2, 3, 1, 2, 3, 2, so on. It goes through sorted order. If you were to just directly like call string compare from C, the possible permutation of all the elements in the set. Specifically, it's kind of interesting to see how numbers are like bubbling up. So we're trying to move down to go through all of our possibilities. We have this possible swap that resets everything. But bring one up a character and we go through all these possible operations.
I think that on the grading with not there. I assume that they'll look at them, they'll be like, if you don't have anything. But I don't think we're.
Yeah, my bad.
Are we back on?
Yeah.
Nice. Okay. So for the purpose of this algorithm, we're going to assume that our sequence is sorted. So every element is going to be strictly, or not strictly, but less than the previous element. We're going to have a sentinel element that's just less than everything. It helps us make the algorithm work cleanly without having too much overhead. So this is algorithm L. It's not a lot going on. There's a couple while loops, and we'll kind of go through what each of these steps are doing independently. But it's 13 lines of code, which is very fun to think about. Yes.
You know what the L stands for?
Lexicographic.
Oh.
Yeah, very fun. So let's kind of go through this. So at the start, we're going to initialize J. If J equals 0, this is good. J is kind of our main index into S. If J equals 0, we've reached our sentinel value, which we've made less than everything else. And so there's nothing left to permute. We're done. And so that's kind of like the main core of our while loop. Otherwise, every iteration of this while loop will output a permutation, a unique one. So the second half, which is the bulk of the code, is kind of searching for J's and L's. So we want to find the largest J such that A sub J, are the actual element that we're looking for, can be increased, that we can kind of push it up a bit. So that's what the while loop on 5 and 6 is doing. We're starting it at the very end of the array, -1, and then scanning down until we reach scanning down until this condition no longer holds, and S of J plus 1 is greater than S of J. If J equals 0, this just lets us be like, oh, we've reached the end. Let's break out, continue, and end our algorithm. Then we're going to look for L, which is the smallest amount we can increase A of J by. So ideally, we would like to only, increase it by the minimum possible distance, and difference between A of J and A of L. Once we've done that and we found L, we will swap the two elements. And then our last step is the mechanics of this algorithm will involve you generating a new prefix A sub 1 to A sub J. And the swap has caused you to have a suffix of A sub n all the way up to A sub J plus 1. So we're going to have to reverse that second half to stay within lexicographic order and output our permutation. Any questions about that algorithm? Okay, so here are a few questions that we've removed from this, right? Yeah, so answers are elsewhere. These are a few questions you can think about how to analyze this algorithm. Mainly, what is the delay between permutations? So what is the big O bound between each iteration of the while loop? What is crudely the runtime of this algorithm overall? So how long will it take to output all permutations? And then something that is brought up in the first exercise, how often does this while loop immediately is false? So if you think about, we start J at n-1. So how many permutations is it that S of J is less than S sub J plus 1? So the n-1 element is less than the nth element. Because that affects the runtime of the algorithm significantly. So I have moved this off. Okay. All right. Section 2, algorithm B. So grade permutation allows you to kind of achieve something a bit different. We want to generate permutations in a way where we're only swapping adjacent elements at every iteration. So it's easier to make incremental steps between each change. This isn't guaranteed to happen in a multi-set. And we'll bring an example here soon, but if you consider a graph of all the permutations, all right, so there's a finite number of permutations. If you make a node for each permutation as a graph and then connect an edge between two permutations, if they only differ by one adjacent swap, what enumerating all permutations boils down to is finding a Hamiltonian path within that graph, but multisets can generate graphs that do not have a Hamiltonian path. So if I am given a multiset that of 1, 1, 2, 2, these are all the permutations of 1, 1, 2, 2, and because we have this weird cycle that just immediately only has one entrance and one exit, there's no Hamiltonian path that covers all permutations. So we aren't actually able to generate a great sequence of permutations without handling some special case. So luckily, in practice, distinct sets are usually the more interesting case to work with, and so we don't have to worry about this case that much, but it is interesting to talk about. So the intuition of algorithm P is kind of going through what happens when you want to generate the permutation of n elements. Say you take one element out and you consider the permutation of n-1 elements. Then you are given this, sequence of just 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 2, 1, 2, 3, 1, 2, 1, 3. And we want to just insert 4 into every position, and that's every permutation of 1, 2, 3, 4. So we get a snaking pattern by column, and so we have a sequence of patterns where we start here and we start with 1, 2, 3 and our 4, and we move down to move the 4 to the next position. And so we snake down the first column and then snake back up this column, because the difference between these two is a single gray swap of swapping the 2 and the 3. And so we're able to just snake up and down through all the columns, which will generate our full gray sequence. So algorithm P looks a little more confusing, and there was probably a way to write this without those two statements, but I was tired and lazy. And also this is just how Knuth writes it, which is annoying for a completely different reason. So it initializes some arrays, it checks some conditions, and it kind of jumps around to deal with enumerating permutations in this gray code kind of manner. So we're gonna initialize C, which tracks inversions. Inversions is kind of a weird concept without going through the direct definition of what Knuth uses. In essence, it's the distance some element in the set S is from the position that it was originally in later iterations relative to one element. So if I give you the input sequence 1, 2, 3, 4, the inversion value is 0, 0, 0, 0. You're like, okay, cool. Then I say, what is the inversion sequence of 4, 1, 2, 3? How to think about it is that the 4 has moved 3 positions left, whereas the 1, 2, and 3 haven't moved at all. So the inversion sequence for 4, 1, 2, 3 is 0, 0, 0, 3. If you swapped 2 and 3, that would change your inversion sequence at different indices. So C is tracking that inversion sequence at the current iteration. O tracks which direction we have moved things. So if we have 1, 2, 4, 3, and we want to consider it as 3 moving right, that's how we kind of track, that position moving right versus any other case. It's a bit weird to think about and kind of wishy-washy, but it works, and that's the magic of some of these algorithms. And again, at every iteration, we're going to print out a permutation. The conditions for when this actually breaks is a little more locally defined, so we just break out of the loop later. So we initialize J and S. J is the coordinate within C of J where we're about to change the value, so we're about to make a swap. Such that we hold a couple invariants, specifically that the actual value of C of J is less than J. You might remember me saying, hey, sets are any unordered collection of items. Great thing about sets is we're dealing with finite inputs, so we can just map everything to natural numbers. It's not a big deal. S tracks the number of indices K, such that C of K is equal to K minus 1, where K is larger than J. So this is the number of instances where this condition holds. This will be helpful to kind of keep track of when we need to deal with how large our range searching is when we're kind of bouncing left and back through the string. So this portion A is we determine Q as the value at C of J plus the value of O of J. So this kind of gives us our little offset because O of J will only be like 1 or -1. If Q is less than 0, so we've gotten a negative inversion number, we need to switch directions. We've gone too far off the end. You know, we're at 0, we've gone to -1, we need to go to the other way. So we switch directions at D, and then we just go back to A and try again. Otherwise, we swap the two relative locations within S and print out a permutation. Great. Yes. Yeah. If Q of J is equal, if Q is equal to J, we need to increase S, which increases our range in like any arbitrary location. And then switch the directions if possible. So B falls through D. If you're wondering why I labeled A, B, and D, is because I labeled the array C because I don't know, I'm weird. So then B and D. If we need to increase S, we check whether or not J is equal to 1. In this case, that's hey, we've kind of ran out of indices to go to. And if so, we break, otherwise we increase 1 to increase our range. Then we move on to D, which just switches directions. So we set, O of J to just be negative, which flips the direction, and we step back J a bit to try again. And we go back to A to repeat this loop over and over again. I just said that. I forget what was put where. Awesome. That's about it with algorithm P. We got rid of those questions altogether. So I guess I'll talk about that. So I had questions about like, hey, let's analyze algorithm P. Because the streamlined version of this algorithm actually has some nice results where this step from 11 to 15 is only visited once every n permutations. So it runs n factorial time, but because the streamlined version takes care of some optimizations, that isn't what this is. It was the first computer implementation of the algorithm. You could really say that the delay between outputs was about constant time because once every n times you're actually doing n work, which is fine because you're doing constant work n times, so it's 2n over n, so n or constant, yeah. But apparently the actual result is that part D runs n to the n time, which is far worse and really bad. So that was interesting to kind of find out immediately. But any other questions than that? Yes.
Feels like it would be a line to right servers.
So you might be right, except for the fact that there is not enough memory in there's not enough silicon in the world to make a computer large enough to hold the memory to deal with that call trace. We don't like recursion for those reasons. It's because it's a really nice way to solve problems as an idea. It's a really bad idea to implement them without some nice PL magic that allows you to do tail recursion.
Right, because this is an n factorial runtime problem.
Yes, this is an n factorial. So you're having n factorial call traces of, I don't know, we'll be conservative, we'll say 16 bytes, not that big of a deal. And then it's 16 bytes by n factorial with any reasonable n is already maybe 32 gigabytes with size 13, 14, it's large. I can't do math. I think you could do like a permutation of like 40 without running into issues if you're doing something recursively. I wouldn't trust it. It isn't. Well, we want to do it. It's the same reason like we want to do dynamic programming recursively, if that was introduced to you before. Dynamic programming, you're solving a problem that's usually n factorial n to the n. And so we remember results so that we only have to do like n squared operations. All right, conclusion. So there's a few other interesting algorithms from this chapter. Algorithm T, which is an extension of P in the sense of instead of outputting the permutations, it outputs the array of transitions you need to take to get to a permutation. The reason this is useful is that you can like repeat generating permutations in constant time. So you do all the work once, and then you now have all the data you need to generate permutations extremely fast. Algorithm G, which is way more complicated than it probably needs to be, but really interesting result of the sense of like I'm given subsets of S that meet some condition, which the book calls a Sims table. Surprisingly not related to the game The Sims. And G is a generalized framework to generate the permutations within that table in an efficient manner. And then there's algorithm X, which is not the X that we talked about last week. Knuth just really likes naming things X eventually. It's an extension to the lexicographic permutation, but it's to also satisfy some conditions. So if I want all permutations, say I have a set of the first 15 numbers, I want all permutations that don't start with 1, 2, and 3. And then I don't want permutations that start with 1, 2, 3. So if you were to just run algorithm L, filter it out yourself, you still go through all n factorial permutations and you just do like a constant filter, and it's like okay. What algorithm X ends up doing is it maintains a linked list structure to keep track of available elements in your set at each step to meet some series of tests that you've defined ahead of time. So if at any point, even though 1 is in the set, and we prevent permutations that start with 1, we currently have elements 2 through n. And once we take one of those, our linked list moves to then now include 1 through n. And so this cuts the recursion. This cuts kind of like the branching tree choices down fast so that we get that incremental speed up for each test that we have. And then this is a quote also taken from the book. I don't know, it was funny. And yeah, do we have any additional announcements? No. I'm gonna bother Jeff here soon. He needs to go make a meeting after our paper gets submitted. Oopsie. So any other questions? Any other thoughts, comments? Zoom. Nope. All right. Yeah. All right.
Give it up for Sam.